Question number 1. Explain why pure substance exists as a solid at low temperature, but changes to liquid and then to the vapor phase at high temperature. So this question is about the stability of different phases at different temperature. The stability of phases is determined by chemical potential, and the chemical potential is a molar Gibbs energy which obeys fundamental equation, that is du mu is the chemical potential change. It's negative Sm dt plus Vm dp. All right. If we want to look at the temperature dependence, then let's ignore pressure, and so that tells you the d mu derivative of dt should equals to negative entropy. So the entropy tells you how fast chemical potential changes with temperature. Note that gas phase has the highest entropy, and therefore the slope is the largest. So gas phase largest chemical potential slope, and then liquid, and then solid. So here is the plot of the chemical potential with temperature. Note that the slope for the vapor phase has the highest slope, largest slope, because the entropy is the largest for the vapor phase. And then the liquid phase. And the solid is this one. This one has the smallest entropy. The slope is the smallest in this chemical potential temperature curve. Okay, and at low temperature, for example, here, the most stable phase is the phase with lowest chemical potential. That's the solid. So this tells you solid is the most stable phase because it has lowest chemical potential at a low temperature. When you increase temperature, for example, to here, you can see the liquid becomes the most stable phase because liquid has the lowest chemical potential. When you increase temperature further, eventually the gas phase becomes the most stable phase. Note these two temperatures. This temperature is the free fusion temperature. This is the temperature when the solid becomes liquid. And this is the boiling point where the phase from liquid becomes the vapor phase. So here explains our first question, the stability with temperature for different phases. Now let's look at the second question. Explain why impurity lowers the freezing point, but increase boiling point. Okay, so to answer that question, we need to know what happens to the chemical potential when you have impurity. We learned that if you have impurity, the chemical potential of A in the mixture, the liquid, should equal to the A of liquid when it's pure. Okay, this symbol means it's pure, plus RT ln XA. Okay, so this is non-pure. This is non-pure. Okay, mixture. And this is pure. And this is the difference. Because XA is always less than 1, so this is always less than 0. All right, and that equation tells you the chemical potential of A when it's not pure should always less than chemical potential of A when it's pure. In other words, whenever impurity is added, chemical potential always decrease. So what happens to the plot? This is the liquid when it's pure, okay, chemical potential when it's pure. When you add impurity, it becomes lower, and so it moves to here, to this line. So this is impure mixture. Okay, so now where is the new boiling point, new freezing point? And you can see here, this will be the new fusion point, okay, and this will be the new boiling point. And from this you can see freezing point becomes lower, boiling point becomes higher. This is a new freezing point. Question number 2. Calculate the freezing point of a glass of water of volume 250 cubic centimeter sweetened with 7.5 gram of sucrose. Okay, so we know that for pure water, the glass of water, the freezing point is supposed to be 0. But now when we add the sucrose, the water becomes impure, becomes a mixture, and therefore the freezing point should decrease. Now decrease by how much? Here is the equation. Delta T tells you how much temperature decrease, freezing point decrease. Is a constant times molality of the impurity. So B is the molality of the impurity, which is moles of impurity per kilogram of solvent. Solute. So solute here is in impurity. So we have grams, molar mass. We can calculate the number of moles. And so here is how we calculate molality. 70.5 divided by molar mass. So this is the moles. Number of moles of impurity, and divided by kilogram of solvent. The solvent is 250 cubic centimeter. We know the density of water is 1 gram per cubic millimeter, which is centimeter. And so you have 250 gram. That give you 250 gram. And that is 0.25 kilogram. Okay, by dividing by this number, you have 0.0876 mole per kilogram. That's the molality. Plug in, delta T is calculated to be 0.16 Kelvin, which also is equals to 0.16 Celsius. And what is the new freezing point? Is the original initial freezing point minus how much change, and that gives you negative 0.16 Celsius. Question number 3. The osmotic pressure of an aqueous solution at 288 Kelvin is 99 kilopascal. Calculate the freezing point of the solution. Now, from last question, we see that to calculate the freezing point, we need to know the molality of the impurity. And the last question tells you how much sugar is added. From there, we calculate the molality. Here, we don't know the grams, we don't know the volume. How do we calculate the molality? How do you do that? Well, there's one additional information, and that is osmotic pressure is 99 kilopascal. Osmotic pressure is a measure of impurity. The equation is this one. Okay, this is osmotic pressure is moles of the impurity, the solute, volume of the solvent, and R times T. Okay, and to modify this equation, okay, we can calculate the moles of impurity divided by volume should equals to pi divided by RT. So pi is given 99, all right, and the temperature is given here, and so you can calculate N divided by V. So N divided by is moles per volume, but we want to calculate the moles per kilogram. So in order to calculate kilogram, the volume should times density. So here is calculated by number of moles divided by volume times density. Now this is already known to be 41, so all you need to know to do is divide by the density. Okay, and this is the density, 1000 kilogram per cubic meter, and that gives you 0.0414 mole per kilogram. And the rest will be the same as the last question. Delta T is K times molality, which equals 0.0769, and then using 0, the initial freezing point minus the change, and that gives you negative 0.0 77 Celsius. So this question is similar to last question, but we need to use osmotic pressure to calculate the molality first.